where are we? So what have we done so far? You know, we started here on the left-hand side with Introduction to Cryptography stream ciphers. Then we did the data encryption standards the last 2 weeks, and today and next week we're going to talk about AES, the Advanced Encryption Standard, which is in terms of real-world impact, Wichtigkeit of this course, is probably the most important cipher. This is the most popular crypto algorithm on planet Earth at the moment, okay? What we have to do for AES, though, and this is very different from DES, we have to introduce a new type of mathematics. So we have to introduce a new number system, and I strongly assume the vast majority of you haven't been exposed to that, so you don't really know what I'm talking about, but that's why I'm here, what I'm paid for. So the main topic today are FF, which stands for finite fields. Okay, so mainly the lecture today is finite fields. In order to keep it more interesting for you, there will be a one. Können wir leise sein? Oben. There will be a 2-minute motivation today why we're doing that. Okay, so this is very short, chapter number 1. Chapter number 2 is Introduction to Finite Fields, kind of the definition. This is really boring stuff for some of you. Then we're going to talk about prime fields and extension fields. In particular, what I'm going to show you how to compute, how to do arithmetic in very strange type of number systems, very different from what we are used to. Okay, so that's the introduction. So we start with chapter 1, motivation. Really motivation for today, if you wish, right? So you know, try not to fall asleep. I'm going to do all the mathematics here. So what we really want to know is how does the most popular crypto algorithm in the world works? And extremely high-level view on AES is this here. 120 bits I and O, input-output. You have a key, and that's actually in terms of I/O behavior, that's one of the major differences with relatively to DES. You support 3 key lengths, and they're much longer than DES. Okay, cryptographically speaking, much more longer. Okay, so we would like to know how does AES work inside. It's in pretty much every web browser that's out there, many banking machines, many WLAN router, Wi-Fi routers, and so forth. So it's super popular algorithm. It has the important, if you really want to understand that, there's an important drawback, if you wish, that all internal operations, of AES are based on finite fields. That's the whole motivation. So if you want to understand AES, you know, and it's somewhat similar to DES, so you have S boxes, you have something like a permutation, but all this stuff is done by doing funny arithmetic, okay? Strange types of computations, which are very unusual to most of you here, okay? And that's why we can, today, we're not really talking about AES and cryptography per se, but we talk about mathematics, a very specific type of aspect of discrete mathematics, which brings us to chapter number 2, Introduction to Finite Fields. Okay. So first, little bit terminology, Namensgebung, terminology. Finite field is already a fancy sounding name, but there's a much nicer name for it. That's synonymous. This is synonym to Galois field. That's a nice French name, right? Okay. So when you want to tell your girlfriend or your boyfriend or your mother, whoever you want to impress, what you did today at the university, you say, I learned about Galois fields, okay? And that's one homework, and which I'm not going to check. Please, Wikipedia Galois, Évariste Galois, very exciting story, life story, very interesting. He died with 21 in a duel. So it's a cool story. Okay, so look that up on Wikipedia. Won't be on the exam. Okay. So if you want to understand. Finite fields, first you have to it's good to know what a field is before we switch to finite fields. In order to know what a field is, we have to look what a ring is, and if you want to understand rings, we have to know what a group is. So what is kind of good to know is that there are three basic algebraic structures. Okay, so the three type of things, basic things people look at in algebra. The simplest thing you can construct is a group, okay? And the definition of the group, did you do groups in mathematics? Was that introduced? No? No, good. So you're going to have that next year in discrete mathematics, so hear much more about that, and we only have 90 minutes to do everything. So we did formally introduce a ring, and a group is an even simpler structure. So very, very, very roughly speaking, a group is a set of elements with two operations, really with one operation, plus, but then you always have the inverse operation, which is the minus, okay? And certain types of rules. In particular, it's you can see that rule number 1 that the operation is closed. Rule number 2 is that the operation is associative, so it doesn't matter in which sequence you do the operation. Rule number 3 is there's a neutral element, the eins element, the one element if you have a multiplicative group. And you have rule number 4, you have an inverse element. So these are the 4 basic rules, and then you can also have a commutative rule. So this is the group, this is the most basic one. We are not interested in a group, okay? Können wir leise sein da oben? The next complex structure, now what we're going to do, we keep the set, we keep a set of elements, but we keep adding operations to it. So this is only plus and minus, so let's add plus, minus, let's add multiplication. You get a ring. One thing that is missing in a ring, and we did do that in the first or second lecture I believe, is that not all elements have an inverse, multiplicative inverse. So that means you can always multiply, but often you cannot divide. So not all elements, you cannot divide by some elements. In order to complete that, to get this fourth basic operation, which is division or inversion, you need a field, okay, which we call F here, abbreviate by F. So what you have in a field is you have plus, minus, times, and inverse. So you have the 4 basic operations, okay? And an elegant way of expressing that in terms of groups is here, okay? formal definition of fields. That's definition 4.32 in the textbook, okay, which you see at this very moment on the screen. And the basic thing that you do, you start with a group. You know, we had this essentially 4 properties of a group, or 5 properties here, right? And so what you do now with respect to addition, and what you do now, you take a set of elements and you say, okay, with respect to addition, you have an additive group. And then, you know, this is the first bullet point. And then you say, the elements also form a multiplicative group here, okay? And you also have inverses. That's the basic idea. So you have one set of elements, and you say, okay, the group laws for additions are fulfilled, and the group laws for multiplication are fulfilled. And that's the idea, okay? Very informally, sehr umgangssprachlich, okay? Very informally, what a field is, a field is a set of numbers in which we can add, subtract, multiply, and divide. End of quotation mark. Zitat, Herr Paar. Okay. Examples. Is our beloved set of real numbers. We all know that. You know, in R we can do all arithmetic. And since we're an electrical engineering department, we also really know pretty well what the complex numbers are, right? So this is another set of numbers, and they also form a field. So the real numbers are a field, complex numbers are a field, but for instance, the rational numbers are a field. The natural numbers, n or z, n or z are not a field because, for instance, normally you cannot divide. Most numbers don't have multiplicative inverses. Okay, so it's not that you can take any set of numbers and say it's a field. Many sets of numbers you don't have all these 4 arithmetic operations available. Okay, so this is super fast what we're doing at the moment. I know, and there will be in the exercises, Dayun will do the things a little bit slower with you here, but and also in mathematics he will do that. For our purposes, this is okay, just to have this very rough hand-waving, very inexact definition. What is important to know at this moment, and a lot of people do that, for instance, in mathematics, even in high school mathematics, some teachers introduce that. Oh yeah, who had these structures? Who had heard about the structures in school? That's a good question. Who heard about groups in high school, in gymnasium? 1, 2, 3, a few people, okay. So very few people do. A lot of people do that, or some people do that at the beginning of college mathematics, of university mathematics. You do hear about that, and then when you do engineering, you don't really need that. I mean, that's the main reason why we don't do that in our electrical engineering education. What is now very specific to crypto, and this changes the complete story, is we're not interested in fields per se, but we're interested in crypto. We almost always need finite sets one feature of the real numbers, the complex numbers, there are many of them, right? Infinite many, right? The infinite number of real numbers. There are many, 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 right? You cannot end, you will never end when you start counting them. In cryptography, this is a general statement. Almost always, you want to deal with a finite set of numbers, okay? So you don't want to have infinite many, but you want to have, for instance, in AES, believe it or not, you want to do computation in a set with exactly 256 elements, okay? We want to do mathematics in a set with 256 elements, okay? Which are fewer elements than there are in the real numbers, obviously, right? In the real numbers, you have many, many elements, many, many numbers. In cryptography, we want to have these things. How can I compute with 256 elements, okay? So, and, oh no, we're still with this definition. And now it's getting, so now if you just step in now in the room, that's perfectly fine, you didn't miss much, but now it's getting interesting, okay? So whoever is not paying attention at the moment, this number, yeah, you pay attention, it's really important, okay? And this is very, very strange, okay? Now we want to have, please listen, please listen. There's a lot of material for 90 minutes. Don't do that on the weekend by yourself. Don't work through chapter 4 by yourself. You don't want to do that. It will not be 90 minutes, okay? Please. So the goal now is, you know, we had this funny rules, you know, all the rules that the field has to fulfill here. And now we want to have a finite number of elements that fulfills that, okay? And there's a very weird existence theorem of existence, okay? When and what are the conditions to construct a finite field, okay? And this is theorem. Welche Nummer ist das? 431, ne? 431, 4.3.1. Okay. What this theorem tells us is finite fields FF only exist if they have p to the m elements. This is a very strange statement, okay? And I give you a few examples what that is, what that means. Example. First example is, we could say there is a finite field with 11 elements, and we have a name for that. We call that GF11, Galois field 11, okay? And why is that? Because what is P and M? I should have explained that. Sorry. So P is Primzahl. P is Primzahl, and M is a positive integer. Okay, so this is and 11 is 11 to the 1, right? P is 11, M is 1, so this is fine. There's also finite fields. There exists a finite field with 81 elements, which you can write in this just notation. You can say, well, this is GF81, but some people like to write it in this form. Look here, P is equal to 3, exponent is also equal to 3, with a coincidence. You could also do 9. Okay, 3 square is also, GF9 also exists. Another positive example, so to make sure you get really bored, there is a finite field with, 3 times 4. Danke. Even a better example. So now it's getting interesting. Okay, so this was following this really stupid simple expression, right? Now it's getting a little bit interesting. We looked at one extreme case is 11. Means we picked the smallest possible m, which is 1, okay? And now there's a very simple question, but I want to have a good answer from you. What is the smallest possible prime that we can choose? What is the smallest possible value for p? 2. The smallest prime number is 2, okay? So, and there it turns out that these are super, super, super important fields in practice, not mathematically speaking. There is a finite field with 256 elements, which is denoted as GF256, or, and that's the notation that we prefer in this course here, GF2 to the 8. Remark, this is the AES field. Okay, that's a name I invented. So this is a finite field, this is the Galois field. This is the Galois field that's being used in your web browser, whether you like it or not, okay? It's built in. There's arithmetic, there's a library for arithmetic, for computation, and this finite field is part of your web browser, okay? So by now it seems it always works, and of course it doesn't always work. You know, there are plenty of counterexamples, Gegenbeispiele. There isn't a finite field with, what did I pick? 12 is a nice example. You know, 11 works, so what happens at 12? Well, if you look at the prime factorization of 12, die Primzerlegung, you get 2 squared times 3, which is not the form p to the m, right? This is p to the m, p1 to the m times p2, right? It's a product of 2 primes, right? So there is no finite field with 12 elements. That means you cannot construct something like this with 12 elements. You know, you can call them A, B, C, D, up to whatever the 12th letter is, L or so. And you cannot come up with rules of combining these 12 elements, these 12 letters, that fulfill all the required conditions for a field. Okay, I know it sounds a little strange, but this is just a fact of life. Okay. From this definition, again, this is very important theorem. From this definition, we can distinguish between 2 types of finite fields. So they all must have this form. So they're all of the form GFP to the m by definition, prime raised to an integer power. Okay? And now we distinguish between 2 cases, namely the special case m equals 1. This means we're talking about fields GFP. They sometimes just refer to a GFP. And the correct name for those fields are prime fields, which makes perfect sense. Primkörper, okay. And on the other side, the only other case that is distinct, well, not the only other case, the most global, the most broad classification is if m is 2, 3, 4, or 5, and so on. If it's an integer larger 1, then we have true fields GFP to the m, and they are called extension fields. Okay. And in cryptography, we are very interested in prime fields and we're very interested in extension fields. Okay. We love both types of fields. They're both important for us. Okay. And here is, as a remark, the remark is underneath the extension fields, especially important in crypto is one very specific type of fields, namely with the smallest possible prime number. This is a good example if p is equal to 2. So we are in particular interested in GF2 to the m. Okay, it's a very, very important practice. And I got my PhD thesis, my dissertation was on that a long, long time ago, so I thought they were cool back then. So, one PS here, one addition here. I forgot. Some people say Galois field in German, and this is really not the correct expression, or Galois Körper. So the German expression here, I just want to add that. In Deutsch it is endlicher Körper. Okay, a finite field or Galois field in English is endlicher Körper in German, and not Galois Körper. Okay, so what I introduced the last 20 minutes or so was essentially this: there's whatever a field is, but a field only exists in this form. A finite field always has this form GFP to the m. And then I said, in particular, we're interested in this here. And now, since the motivation is only AES, we're not doing the theory of finite fields. I mean, there's later on that we have a special course which is 1 semester finite fields. Okay, that means 14 weeks. We do the whole thing in 1 week. It's very condensed. Okay, and it's only for AES, so we really try to extract the essentials, the most important things that you need to know in order to understand AES. What we really want to understand is this here, because I showed you before, within AES, within the Advanced Encryption Standard, there's only one field being needed, namely GF2 to the 8. So that's the goal of the next section. So we're done with introduction to finite field. So what we really want to understand is extension fields, GF2 to the 8. And in order to get a feeling for that, we do prime fields, which are quite easy. Okay, so first we do prime fields, because they're really easy, and you get a little bit for feeling for that. And once you understood prime field, switching to extension fields is hopefully easier. Okay, so now we come to the third chapter of today, namely prime fields. And there is a lot more theory you can do about prime fields, about finite fields in general. The only thing, in quotation marks, in Gänsefüßchen, the only thing I want to do with you is to show you how to compute in fields. okay, in finite fields. So a more exact headline for this chapter is not only prime fields, but prime field arithmetic. Really fancy terminology. So what that really means is, how do I compute in a prime field? Okay, arithmetic is a really fancy term for computation. Okay. So the first statement is, and the first statement is really trivial. What I'm writing down now, you will think, why is Professor Parr doing that? Okay, the first statement is the elements. What are the elements here? The elements of a prime field GFP are the integers in the following set, curly brackets, geschweifte Klammer, curly brackets, 0, 1, up to p minus 1. So this seems almost too trivial, right? It's too trivial. This seems completely straightforward. What else? Okay. What you will see in 10 minutes or 15 minutes, when we switch to extension fields, GF2 to the m, suddenly the elements are not numbers anymore, not integers anymore. Okay, so be warned. Okay. For prime fields, it's very easy. We essentially do computation with integers, stuff we are used to from elementary school, from Grundschule. So what we now want to do, again, we look at a finite field. Finite field is a field, and what I told you before, there are 4 types of operations. There's addition, subtraction, multiplication, and inversion. Okay? And now we want to talk about all 4. How do we do this type of arithmetics, these type of computations? Okay? It turns out that it's, in most cases, is very, very easy to do. And actually, we did that already. You know, we've been doing that for a few weeks. I think I do that here. So that would be 3a, would be add, subtract, and multiply. We do all together. Okay. So we start with 2 elements, A and B, any element of a finite field, and now I'll show you the rules for addition, subtraction, and multiplication. Okay. If you want to add A and B, what you do, you simply do addition and you do modular reduction. Mod P reduction. Okay. When you want to subtract A minus B, let's call that result D. Again, you subtract, you do modular reduction, you're there, everybody's happy. Okay. If you want to multiply A times B, which let's call the result E, again, A times B modulo P. Very, very, very easy. Stuff we did in the second lecture, I think, when we talked about modular arithmetic. Very easy stuff. Okay. Note that all conditions of fields are satisfied erfüllt, you would say in German, erfüllt. Note that all conditions of fields are satisfied for with these computations. What do I mean by that? That sounds kind of cryptic, what I'm saying. So the conditions is the stuff you see here that we, briefly talked about before. We said a field essentially consists of two groups, namely an additive group and a multiplicative group here. And then, and then you have against the group rules for a group that you see over there. And all these rules are fulfilled if you do arithmetic in this way here, okay? For instance, one condition which is easy to check, number one, the group operation is closed. Closed is Abgeschlossenheit. That means if you do A plus B, the result must be in the group again. And of course, we know A plus B can be too big. The result can be too big if you do plain addition. But with the modular reduction, the result is again in the group, so it's closed. Same goes for subtraction and multiplication. And all these rules are satisfied if you do modulo P. And what we're not doing here is, of course, proving that. And everybody who is a mathematician hates my lecture, okay? Because I just give them to you as axioma, right? It says, it works, believe me, right? I'm motivated, but I don't show you why, okay? But this is this is because we have to do finite fields in 90 minutes and not in whatever, 3 or 4 or 5 or 6 weeks, okay? So what I told you here is if you have a prime field GFP, for instance, with an example, GF11, the only thing you have to do is do normal integer arithmetic here, normal addition, subtraction, multiplication, divides the result and takes the remainder, right? This is modular operation. There's one operation left, obviously, right? It's plus, minus, times, mal, and divide, or inversion. So we have to do that, and that we can do quickly. And you remember that from the other homeworks you did in the past, this is kind of special, okay? If you have an element A, in GFP, then the inverse A to the minus 1 must satisfy rule number 4. Rule number 4 for the multiplicative group, that means given is A, now you have to compute an inverse A minus 1 such that the result is equal to 1. Okay, that's the definition. And again, we did that when we talked about the affine cipher, right? The cipher with A times X plus V plus B modulo 26, we did it. Okay, this type of thing. So the big question is, compute how? How do we compute that? Okay, it's very different from before. Here, this is regular arithmetic stuff. You're literally, you've known since 3rd grade, that der dritten Klasse. Here we don't know. We did trial and error. We did, versuchen, right? We did brute force when we did the affine cipher. We don't really know how to do that, and I think we'll do that the last week before Christmas. I'm going to show you a method, an algorithm for doing that. Right now, I just tell you the name, right, which is not very helpful. Can be computed with the extended Euclidean algorithm. Extended Euclidean algorithm. Erweiterter Euklidischer Algorithmus. Chapter 6 in the book, okay? And we're going to do that, I think, in 3 weeks or so, whatever the last week before Christmas is. I think that's the time where we do. Yeah. Very good point. He says, what about the 0? 0 times something equal to 1 never works. And now we can go back to the definition of a field. Namely, here it says, this line is the answer. All elements of F except the 0 form the multiplicative group. Okay? Excellent, was a super observation. Okay? So, and this I skipped over that before. What I essentially said here, a field is composed of 2 groups, an additive group, multiplicative group. That wasn't the whole truth. We need the whole additive group, die ganze additive Gruppe. That means all elements with respect to addition. But for multiplication, we need all elements except the 0. So with addition, all these elements form a group in a field. With respect to multiplication, only these elements, okay? Multiplicative group, additive group. Multiplicative, additive, okay? It's not that super important at this point. If you do that in discrete mathematics, this will be very important. Here, for us, at the moment, it's not that super critical. Okay. So, what I showed you on this blackboard here is that prime fields are actually very, very easy to handle arithmetically. So it's quite easy to do computations, okay? So you might think, well, there was a lot of definition what Professor Parr did today with us. There all the stuff I don't understand. And then when it's getting interesting, doing computations, because you can imagine what your homework assignment next week will be, right? We're doing AES, and you have to encrypt with AES, similar to DES, right? First round of AES, input all zeros, what is the output? All these baby examples we do with you. So from now, at this point in time, you might think, well, there's a lot of overhead, I did a lot of stuff which is not really that important. Now comes the important stuff, and this is super easy, right? This is kind of in 1 minute what we did so far. But the world is sometimes very tricky and mean, gemein, right? Because AES is not based on prime fields. AES is based on this funny field, GF2 to the 8, that means an extension field. And now, hold on to your thing. Extension field arithmetic is very, very different. So now starts really the main part of the lecture. Okay, this was all Vorgeplänkel, all introduction to kind of the main part with respect to AES, how to do arithmetic, how to compute in extension fields, which brings us to section number 4. And we are perfect in the time. So the second half of the lecture is going to be the important part. And sometimes the other way around, we do kind of important part in the beginning and then it gets kind of boring. Here it's the other way around. Fourth and last chapter, which will drag on for 40 minutes or so, is extension field GF 2 to the m arithmetic. And I would really, really, really like you to be quiet. Hello, please be quiet now. This is important. This is in intellectual, this is the most challenging part we've done so far in this course. Please believe me, 45 minutes, pay attention. If you're tired, if you went to bed too late, this is fine, fall asleep, but don't talk, okay? Don't distribute the other 100 students in this room, okay? Please. Let's go back in time 10 minutes. I said, what are the elements of GFP of a prime field? And then I said, it's this trivial statement. Of course, the elements are numbers, right? 0, 1, 2, 3, integer numbers, right? Here starts the confusion. It's the first time we deal with an algebraic set with a finite field where the elements are not plain old boring integers, okay? Namely, this is A, which is already worth a subchapter. Let's call that element representation. Representation. Representation is Darstellung, right? If you want to have an official German translation. Okay. Hold on, this is now a strange sentence. This is going to come to a surprise to most of you. The elements of GF 2 to the m. Oh, by the way, you know, the general extension fields are GF 2 p to the m, but we only need this AES case. In AES, we have GF2 to the m, so we narrow our scope. Wir bekommen enger. Wir machen was sehr Enges hier. We only look at GF2 to the m. So the elements of GF2 to the m are polynomials. That means we look at these type of if you have an element GF2 to the m, you know the extension degree is m. We start with m minus 1. That means the polynomial degree is m minus 1 and the highest coefficient is m minus 1. And then you go down, blah, 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 and at the end you have a1 times x plus a0. Okay. And if you call this here, this polynomial a for an x, a of x, then this a of x is an element in the field. Okay. This polynomial is element of the field. Okay. That's one strange thing. Okay, so now when we talk about polynomials, what is really interesting in polynomials, what are the coefficients, right? Once we know the polynomial coefficients, we want. The coefficients are a0, a1, a2 up to a minus 1. Remember in the AES case, m is equal to 8. Here. So in the AES case, we have a0, a1, a2, 3, 4, 5, 6, up to a7. That's the highest coefficient. So we have 8 coefficients here. So it turns out that the coefficients ai are element of this field here, of GF2, which is what's called a subfield, you know, underneath the Unterkörper. Okay, GF2. But what kind of field is GF2? Is GF2 an extension field? Is that an... No, it's not. Namely, how did we call GF2? What kind of field is that? Very, very good. Excellent. Sehr gut aufgepasst. The prime field. Okay? A very small, very boring, very tiny, small field with exactly 2 elements. Namely 0 and 1. Okay? I'll push that up a little bit for people in the back. So, and now there's an... Should I say that? I'll show you an example, I think. Let's do an example and then I'll talk more about it. Okay? So, okay. So we look at this tiny field 2, GF2 to the third, or 2 cube, 2 hoch 3. What we know is that any element must have this form, a2x squared plus a1x plus a0. Okay. Then, and what are the possible values for a0 here? 0 and 1. What are the possible values for a1? 0, 1, a2, 0, 1. So we have 3 bits. Okay, this is now kind of a computer science viewpoint on that. Forget about algebra and fields and theorems and blah, 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 blah. Properties. Let's look at the element representation. This can be 0 and 1. This can be 0 and 1. This can be 0 and 1. So we can really talk about this, view that if we want, as a vector of bits, a 3-bit vector, right? 3 bits here. How many different numbers how many different things can we represent with 3 bits? How many different numbers can be expressed when we have 3? Yeah? 8, right? 2 times 2 times 2. 8 numbers, this is not bad because we talk about the field GF8, right? The 8 elements, and these elements are represented by 3 bits, okay? And now, you know what I sometimes do here? I say just the elements I put in curly brackets in Mengenklammern here. And that's what I want to do now. I want to show you what are the elements, okay? Well, one element is 0, 0, 0, that's the 0. Another element, the next one, if you do this lexicographic enumeration, you have 0, 0, 1. Okay? It means those two, the two higher, A1, A2 were 0, okay? And then we had this equal to 0, 0 to 1. So the next thing we have to do, we have to set A1 to 1, and then we get the expression, how do I do that? X. This is clear. If I have the polynomial x here, then this is 0, this is 1, this is 0. Okay? Just as a Nebenrechnung here. Everybody with me, all right? It's not very complicated. Okay, so now I'll continue. So if this set, this is still 0, 1, 0. Now I increment this to 1, so I get x plus 1. Okay? The next thing I have to do, I have to increase A2. And the easiest thing is I just have x squared. Then I do x squared plus 1, x squared plus x, and x squared plus x plus 1. Okay. These are the 8 elements of GF2 to the 3. Yeah, is it back up? Yeah, it's working again, right? Yeah, since it's low on battery, so we'll try it. Let me know if it, yeah. Neue Batterien, new batteries, yeah. Trans. Okay. Ja. Gut. Alles an den Kollegen. So, so what I showed you, and this is not deep finite fields, it's just kind of enumerating, durchnummerieren. Eins, zwei, drei, vier, fünf, sechs, sieben. You get your eight polynomials here. Okay? Very simple. So what I showed you, and this wasn't all that complicated, what I showed you here is that what are the field elements is, and then we looked, okay, if you use this polynomial of degree m-1, that means you have m coefficients, a0, a1, up to a-1, and each coefficient is a bit, you get exactly the number of elements you need, okay? So far so good. So right now there hasn't, well, something has happened here. That would be too much to say nothing has happened. So but what we're interested now, the big thing is, and that's the last part of the lecture, is how to compute with the polynomials here, okay? How to compute with polynomials. But I have to clean the blackboard, so you have 1 minute of, you can talk, okay? And nicht aufpassen, schlafen, YouTube gucken. Okay, break is over. Back, full concentration. Now I rephrase the questions I said before. Können wir alle? Der ist hellhöriger, schlecht für Sie, ne? Die Idee, wenn Sie ein bisschen quatschen, ich kriege das kaum mit, ne? Und hier höre ich mehr. Und es nervt mehr, mich und die Kollegen, die Kommilitonen. So, big question is, so we established this is GF2 to the M, this is the stuff that's in your web browser. If you encrypt a credit card with your web browser, if you have a secure connection to eBay or Amazon or whatever, your credit card number or your account number is being encrypted with using AES, the AES algorithm. Inside, there are these polynomials which represent numbers here. And now the question, how do we really do this arithmetic here, to computation? When we talk about computations, again, this is a finite field. We have 4 types of operations. We have addition, subtraction, multiplication, and division or inversion. And again, we do the whole list, right? Given those polynomials, how do we do arithmetic with these polynomials? Okay? And it starts easy, and then it gets more and more unpleasant and more complicated. So B is addition and subtraction in GF2 to the M. Okay. Long story made short. Long story made short is the definition (433). What this tells us, the most important thing is the first equation on, in this box, in the definition. What this tells us is do a regular polynomial addition. So addition and subtraction is just the same as what we're used to. Take your polynomial and add coefficient by coefficient. So it means A0 plus B0, A1 plus B1, okay? A2 times B2 and so forth. This is what your web browser does when the web browser encrypts an email, okay? Or a credit card number or whatever, if HTTPS is active, okay? So use regular. Use regular polynomial addition or subtraction. Okay. So here, actually I was wrong. The most important line is here. CI, or the right-hand part of both equations. So you take AI minus BI for the subtraction, you do AI plus BI for the addition, okay? Very, very intuitive, very intuitive, exactly what you would normally do. If I would give you 2 polynomials and I ask you, please add the polynomials, this is what you would do. There's one important small detail for GF2 to the M, or in general, use regular polynomial subtraction, comma, where the coefficients are computed in GF2 again. That means when you add here at this point, if you add A0 and B0 as an example, you do that modulo 2 because the coefficients are in GF2. So it means the arithmetic of the coefficients are in the subfield. Let's do an example. Again, we use GF2 to the 3. So let's say this is one of the elements. Okay, remember the elements here, it's the same example we did before. So I use this polynomial, and then I say I add that to this polynomial. Okay, or in binary representation, it takes this polynomial from here, and I add that to this polynomial. X squared plus x plus 1 is a, and then the other operand is b of x, which is, if there was 1, this is a plus b. So, and you add now here, okay, and what you get is a plus a x squared plus x plus 1 plus 1. So we would get, 1 plus 1 is 2, I know that, right? Okay. So, but then what I just told you is, this is in GF2, but GF2 is a prime field, and it was here before, right, at this point. And what it says is, in prime field arithmetic is modulo arithmetic. So you do modulo 2 arithmetic here. But what is 1 plus 1 modulo 2? What is the result? 0, right? Exactly. So this vanishes, der verschwindet. This stays, and 1 plus 1 is 0 again, so that means this is x, okay? Bemerkung, and we actually discussed that when we talked about stream ciphers. We had the observation that addition modulo 2 is the same as subtraction modulo 2. Do you vaguely remember? So if you subtract those two polynomials, you get the same result. Addition and subtraction in GF2 to the m are the same operations. So if you do a minus b, you get the same result out. Okay, this is we did that when we talked about stream ciphers. Okay, so it doesn't seem so bad. It really is polynomial addition, adding and subtraction to elements in GF2 to the m is pretty straightforward. Okay, and now probably comes the main operation that is painful, that it's difficult to do. And this is multiplication. Multiplication in the Galois field GF2 to the m. And now things start to get complicated. This is an extreme lecture. It's getting more and more complicated, more and more interesting, more and more. You don't want to do that at home. You don't want to start Wednesday next week, starting doing the homework, okay? If you miss the next 10 minutes, you don't want to miss them, okay? So what we're trying to do is essentially use the same recipe that we did here. Here we wanted to add 2 elements of GF2 to the m, so what we did, we just added the polynomials, of course. And of course, we try to do the same thing. So what our intuition tells us, Intuition, our Gefühl, Bauchgefühl, let's try the same thing again, intuition. Just do regular polynomial multiplication. Again, it essentially worked with addition and subtraction. Wasn't that bad. You just multiply and hopefully we're there. Okay? Let's start with an experiment. Okay? Let's not give a theorem, but let's start. Let's look what's happening. Again, we use GF2 to the 3. We want to multiply a times b, and we take the same polynomials as before. Why not? So, but we're not adding the polynomials, we're multiplying the polynomials here. It's x squared plus x plus 1 times mal the other polynomial times this here. You can take any other polynomial, okay? But this gives nice examples for the blackboard, okay, if you use this example. So what you're now going to do is you multiply, right? Ausmultiplizieren, okay? So first I take x squared times the other polynomial, so you get x to the 4th plus x cubed plus x squared. Plus x squared plus x plus 1. Okay. Seventh grade, okay, ausmultiplizieren. Okay, this is not complicated. So now it's getting a little bit complicated. x4 is okay, x cubed is okay. What happens with x squared plus x squared? What is this here? The same that we had here is 0, right? It's okay, one more line. This is 1 times 1. This again cancels out. Das löscht sich aus, right? It's 1 plus 1 is 0 modulo 2. So this is equal to x to the 4 plus x cubed. And now I hope everybody is awake, nobody is talking. I hope nobody's looking at the Apple laptop, and okay, very good. Watch out here. So it seems everything worked out. What is Professor Parr talking about? It wasn't that hard, right? This was 7th grade math. Where is the problem now? Why is this not the correct result? Where's the problem? It's not in the field. Field stops here. Right here, 8 elements. GF 8, the 8 elements, x to the 4 plus x to the 3rd plus x plus 1 is not in the field. We have a problem, okay? This is why multiplication is complicated in finite fields, in extension fields, okay? So, how did we Ausflug? Let's go back to prime fields. How did we deal with that with prime fields? Let's say we do GF7. We were in a similar situation, right? When you multiply, it takes the elements 3 and 4. They're in GF7. You multiply, you get 12 out, right? 12 is not in the field here, right? The field elements are only 0, 1, up to 6. how do we deal with that situation? What did we do? What was the magic thing we did? We did mod 7, exactly, modular reduction. So this is, okay, so, and the same idea applies to extension fields. We want to do modular reduction, but now you cannot do modular reduction mod 2 or mod 7 or mod 4, but you have to reduce modulo what? Modulo what type of object do we have to reduce? Any ideas? Yeah, power of x, exactly. We have to reduce with a polynomial, okay? To get a polynomial smaller, if you wish, you have to divide by another polynomial and look at the remainder. And this is what we're doing. And let's give this a name maybe at this point here. So we call this here. You know, the final result will be C, right? A times B is equal to C. But this is not, we're not quite there yet. That's what we call that C prime, C strich. Okay, that's the intermediate result, Zwischenresultat, okay. And now let's solution to this situation, to this problem is reduce C prime of x, C strich von x, modulo a polynomial. And now the question, what kind of polynomial? Let's go back to here. For a prime field, this was always modulo 7. And what type of number is 7? This is a prime, right? So what we want to have now is prime polynomials, so polynomials that you cannot divide, right? And I don't know why, and they're not called prime polynomials, which would make perfect sense, but they're called modulo polynomial that, in Gänsefüßchen, in quotation marks, that behaves like a prime these are called irreducible polynomials. Okay, so what do I mean with they behave like a prime? Surprise, surprise, you cannot factor them. You know, 7 cannot be factored, it's a prime, and if you look at 15 is 3 times 5, right? It can be reduced, it factors, so this is not a prime, the same here. If you want to do modular reduction at this point, you need a polynomial that cannot be reduced, that does not factor, and this is called an irreducible polynomial. So we irreducible polynomial for g of 2 to the 3 is we call that we always in this course we call that p of x, and other people call that differently. Is p of x on the irreducible polynomial is x cubed, x hoch 3, x to the third, plus x plus 1. So, the formal definition is here, and this definition is, so what we want to multiply A times B. So the first thing that this definition tells you, you need P of x, and P of x is an irreducible polynomial. Okay? That's the first thing that you need. It's similar to a prime field, you need a prime, right? You need P equals 7, so otherwise we cannot do calculations. Same here. If you have that, things become pretty easy. You do A times B. This is what we did so far, right? A times B. And then the definition tells us, oh, by the way, afterwards you also have to do modular reduction. And this is what we're going to do now when we continue with the example. So you do, now we start with C of x here. X to the fourth plus x cubed plus x plus 1. Divide fourth grade, right? Vierte Klasse. Division. You divide by x cubed plus x plus 1. We need 5 more minutes, please. I know it's really hard being concentrated, not talking for 90 minutes. Please, the last 5 minutes. Again, I completely understand if you cannot concentrate anymore. It's really hard. Frontalunterricht, 90 minutes is very hard. You don't need to, but don't talk. Don't talk! I mean, I'm just... Bitte. Ich sage, es ist schwer, ich verstehe das. Noch 5 Minuten. Oder gehen Sie leise raus, ist auch okay. Schreiben Sie ab, gucken Sie auf Video an nächste Woche oder so. Please don't talk. Okay. So, what you do now is, you look polynomial division by hand. So we do that. Well, first we want to get rid of x to the fourth. So what we do, we multiply this highest coefficient by x. So this is x times x to cube is x to the fourth plus x squared plus x. Okay. Then you subtract here, but we also know, because we do everything GF2, the nice thing is normally you have to subtract here at this point, but you can also add. So it's a little bit easier just in terms of notation to do addition here. X to the fourth plus x to the fourth is 0. This is x cubed plus x squared. These two x's, they cancel again. Die löschen sich aus. Plus 1. Okay. We can continue. So we have x hoch 3 is still too big, x cubed, right? We want to get down here. Okay, so we can do one more iteration. Plus 1. That means we add this polynomial. So this is x3 plus x plus 1. Again, we add, and the result is this here. Okay. So what we've done so far here, so this was A times B. This is P of x. And this is what you have at the bottom of this algorithm. This is the result. So this is A times B mod P of x. Okay, so this is the result of our computation. So one question that might come up at this point is, where do I get this polynomial from? Okay, so there's maybe one remark here. For every field GF2 to the m, there are several irreducible polynomials. That means there's more than one, which is kind of unusual, okay, which is different from the prime case, from prime fields. If you want to have the field GF7, there's only one prime number 7, right? There's not a 7b or something, you know what I'm saying? So there's only obviously one prime number. It's different here. So we have, for instance, this is a irreducible polynomial, and I'm not 100% sure, but I think this is irreducible too. Okay? And now, and this is in just, we're not used to that. If you have a given finite field, let's say GF2 to the 3, the results of your computation depend on the irreducible polynomial. That means if I tell you, please compute something in GF2 to the 3, you cannot do that if I don't give you the irreducible polynomial. Because if you do this operation with this different p of x here, right, you get a different result out. Okay? So that means for a given finite field, if you actually want to encrypt with AES, for instance, you need a polynomial. Okay? And believe it or not, this is part of the AES standard. And I call that the AES irreducible polynomial is the following. Since here we're dealing not with GF2 to the 3, but GF2 to the 8, P of x is x to the 8 plus x to the 4 plus x cubed plus x plus 1. This is not totally unimportant, okay? I don't know whether you have to remember that by heart, auswendig lernen, but it doesn't hurt, okay? It's not the worst thing if you remember that, okay? So we're almost through. Only the very last thing. Oh yeah, what's missing? Does anybody paid attention the last 90 minutes? Which operation is missing? Inversion or division, right? And you will be relieved we're not really doing that here. We're not doing division, okay? I just want to give you the definition so that you heard it, because it does play a role. So D would be inversion in GF2 to the M again, also wie zuvor. The inverse a to the minus 1 of x of an element a of x in GF2 to the M must satisfy, and what we're really doing is, that's a nice thing about mathematics, it's very logical and stuff. Inversion by itself, this element is defined via multiplication. You say it takes this element times its inverse has to be this, in case of multiplication, be equal to 1. So that means inversion is defined via multiplication. That means you take a of x, and if you're looking for the inverse, you say, okay, the inverse, this element, what I'm looking for, must fulfill, must satisfy, muss erfüllen this condition. This must be equal to 1. And you do a multiplication. And how does multiplication work? Well, multiplication works mod p of x. Mod p of x, okay? And the question is, how do we, given Given one polynomial a of x, one field element, how do we find that? Again, this is what we need here is again extended Euclidean algorithm. You were great today. Thank you very much.